Okay, so I was given the title Topics in Topological Graph Theory. And I think with all of these sessions, you've got some huge area of graph theory to talk about. And there are lots of different directions you can go. So thinking about this today, I thought for the starting point, I would kind of assume minimal background. So I know that lots of people have different levels of experience. So really, I don't want to assume more knowledge than really undergraduate graph theory. And by doing that, I hope to emphasize kind of the natural development of ideas in topological graph theory. So I'm going to just start off with some very familiar ideas. And in sort of wondering where to go, I had sort of two choices. And one, I could go down kind of the well-established route and talk about sort of the kind of main biggest topics in topological graph theory. But thinking about what this is, and it should be a research-oriented school, I thought I could also go down maybe not quite the main route, but look in directions that will take you quite quickly to kind of open and accessible research problems. Not necessarily just because it's an easier area, but just because there's been less development, it's a younger area. And sort of by the end of this talk, I hope to have sort of explained enough so you can, pose and prove your own original research work. Okay, so let's start right at the beginning. So my essential background. So these are the things that you know before. So first of all, I will say up front that my graphs are always going to be allowed multiple edges and also loops as well. So I'm not just considering simple graphs, and the fact that I can have these in particular loops is really important to recording topology. I want you to keep in mind some standard graph operations. Okay, so almost certainly you have seen these before. And the first one is just deletion. And by deletion, well, deletion, I can either make this act on some edge of a graph or some vertex of a graph. And essentially, all I'm going to do is throw this away. So for example, if I've got my graph G here, and I've got my blue edge E down here, then G delete E, I just throw it away. And I can also delete vertices. So if I want to delete this vertex V here, well, I just throw it away. But of course, all of my edges must meet vertices. So I've also got to throw the other two edges away, this one and this one here. So I can do my graph G delete V here as well. Okay. What else have we got? Well, the other standard operation down these lines will be edge contraction. Okay, and the idea here is that I've got some edge in a graph, and it's got its two ends, and all I'm going to do is I'm going to identify the edge and all of its ends into a single new vertex. So when I make this one vertex over here, then I'm going to end up with this new red vertex here. And I've got my graph here that I'll denote by G contract E, so with this overline there. Okay, so I'm sure most of you will have seen these operations before. If not, they're not super complicated and you've seen them now. Okay, so these operations of deletion and contraction are sort of more form the mainstay of sort of structural graph theory, if you like. And in that direction, sort of a graph minor is basically you start off with some graph G, you delete and contract some edges and vertices, and you end up with some other graph, and that's going to be a minor of your graph. So a graph is a minor, H is a minor of G, if it's obtained through the operations of vertex and edge deletion, and as well as edge contraction. Okay, so this is sort of one aspect, one of our starting points. So let's keep going with these standard kind of concepts you'd meet in your first course in graph theory. Okay, so we want to talk about topological graph theory. Okay, so I know I'm going to have to deal with topology in some way, and kind of the very first step of the origins of this are just in about drawing graphs in the plane, or more accurately, sort of embedding them in the plane. So what we've got here is we've got our plane, R2, and I'm just going to draw my graph in it, and for each vertex of my graph, I'm just going to make it a point, and whenever I've got an edge between them, I'm just going to draw some line or some curve between the corresponding vertices for the edges. And kind of an important one is that when I draw this, I'm not allowing the edges to cross. Okay, so there are some graph drawing problems where you do allow edges to cross, but here we're doing topological graph theory, so I'm looking at graph embeddings, so I'm never allowing my edges to cross each other in my drawings. There is also one other condition down at the bottom here, and that's that every face in my drawing must be a disk. Okay, so coming up to our example here, what does this mean? Well, if I take the plane and I take a pair of scissors and then just start cutting the graph open, or the plane open along this graph, what am I going to get? Well, I'll get this solid shape here, solid shape here, here. And these are just homeomorphic or equivalent to just disks in R2. Well, okay, so I'm drawing in the plane, so there's one little annoying condition here, is that when I cut out my graph, this outer thing here is no longer going to be a disk. So if I'm drawing them in the plane, I have an annoying condition that everything is a disk, except for exactly one of them, one face, which is just R2 minus a disk. So you've got this kind of special unbounded face. And that's kind of a little bit annoying to deal with, and we'll see how to get around that later. Okay, so just to absorb this definition, with this example here, my graph is connected in blue, so I could just, as a straight up question, just ask, well, what about disconnected graphs? So if my graph, let's keep it nice and simple, I suppose my graph had two components, this one and this one, and I wanted to get an embedding of this in the plane. Well, kind of the natural thing to do would be to just draw both of these on the page, but this goes wrong, and the reason is that this cellular condition doesn't hold. And if I look at the outer face, what have I got? So this area shaded in green. When I cut open the surface along the graph, I'm going to end up with a region that's just the plane minus, but it's missing two disks, so it's got two holes in it, and this definition only allows me one hole. So I can't just draw them both in the plane. So in this situation, when I've got more than one component, I must draw them in different copies of R2. So each sits in its own plane. Okay, so again, not such a major issue when we're dealing with plane graphs, but it will come up a little bit more later. Okay, so hopefully everyone's all is good so far. I'll try and monitor the chat. So if you want to ask any questions during the talk, please just pop it in the chat window and I'll try and pick it up. and answer them. Okay, so we're drawing our graphs in the plane, and some straightforward observations is that, well, first of all, not every graph can be drawn in the plane this way. And the classic example would be the complete graph K5. And if I try and draw this in the plane, so I've got my 5 vertices, and then when I try and draw in all of the edges without crossings, what happens? How many can I draw? So I could maybe do that one round there. And then maybe, oh, if I try and draw the edge from this vertex to this vertex, I see there's no way I can get to it without crossing some other edge. So K5 is one of your classic examples, and one of the really important examples of graphs that you just can't draw in the plane. And maybe one thing to notice here is that kind of behind all of this, this argument about not being able to draw this in a plane is you've got Jordan's curve theorem, which just as a reminder just states that if you take a simple closed curve in the plane, that curve has both an inside and an outside. Okay, so one observation is we can't draw everything in the plane that way. Another thing is that even if we take a graph, so one graph, so let's take a really nice, simple example of a graph. Let's just take one vertex, and how about I take 3 loops like that? This is about the smallest example I can think of that will work. And then if I look for embedding this in the plane, well, there are various ways I could do this. So I could put my vertex like this, and I could essentially draw it like I've drawn it up here. So I could draw it like I guess like a flower, like so. Or maybe something else I could do is I could draw my vertex, but then I could have 3 nested loops like this. Okay. And these 2 drawings, or these 2 embeddings of this graph, are not equivalent to each other. Okay. Why are they not equivalent? Because there's no way I could deform the plane, so no homeomorphism of the plane that would take me from this graph to this graph here. And we'll come back to these issues later in the talk, but it's useful to remember that these kind of subtleties are lying under this, this situation, even the simplest case of plane drawings. Okay, but what can we pick up for this? So I'll come back more to these issues, as I said, but for now we notice that even with this classic situation, these classic undergraduate examples, there are really 2 directions that the theory has taken us. And one is to think about graphs in the abstract. So your graphs are sets of vertices and sets of edges, and look for the properties of the abstract graph that say when they can be drawn in the plane or embedded in the plane. But the other direction is that what you could do is you could consider the graphs that are actually embedded in the plane. So you're working with this graph that is embedded in the plane, so this embedded graph. So, and these are kind of 2 directions of graph theory. And today, given time, I hope to be able to say something about both directions, but I'm going to kind of primarily focus on this side here and working with graphs that already have some fixed embedding in the plane. And maybe just a little bit of terminology that I won't use so much, but it's kind of what the terminology in the literature sort of reflects this subtlety. And this is often overlooked in that sort of when you're talking about a plane graph, that's some graph that's embedded in the plane, whereas a planar graph is one that can be embedded in the plane. Okay, so there's kind of a little distinction, a little subtle distinction that often gets kind of blurred in the graph theory literature. So just checking the chat window. So there's a rather excellent question about if there's a sufficient condition or a necessary and sufficient condition about telling when a graph can be embedded in the plane. There most certainly is. And as in the chat window, there's Kuratowski's theorem. And if we go down this direction, I'll talk more about that and its generalizations. So you can put that question on hold for the moment. Okay, so we've been talking about plane graphs and planar graphs, but my training was topology, so I don't think there's anything special about the plane. Well, I suppose the only thing that's special about the plane is that it's super easy. So we could start asking ourselves with these questions is sort of why the plane? Why draw them in the plane and not on something else? So what I'm going to do is just give you a quick reminder of surface topology in case you haven't seen it before, and a quick overview of the main ideas. If you have seen it before, you can probably just relax for a few more minutes. I'm not going to be saying anything that is kind of not standard. I'm also going to avoid formal definitions because, well, it can be a bit of a pain. So a closed surface is just some topological space in which every point looks locally like the plane. And some of the usual examples would be sort of the sphere, which is drawn down here, or the torus, so the surface of a donut, two torus, so sort of two donuts glued together like this. And kind of the point is, so this local condition sort of means that if I focus in on one point, then when I zoom in, I kind of see that I've locally, my area sort of looks like a flat disk, or it looks like a copy of R2. So it sort of locally looks like R2. Okay. If you really want a definition of this, you could say it's a non-empty Hausdorff second countable topological space in which each point is locally homeomorphic to R2. But, well, for all intents and purposes, we don't really need to get into the formality of the definition. We can just work with this informal definition of the locally looks like a plane. Okay, so the other thing we need to know is that surfaces are considered up to homeomorphism, again, avoiding a formal definition, but homeomorphisms say essentially that, well, if I have my torus here, then I can sort of push it around and deform it, so I think of it made of rubber, but I also have the option to take some scissors and cut it open and re-glue it, as long as when I stick it together, points that were close before I cut and glue are still close together once I stick it back together. Okay. So it's kind of, I'm allowed to do any operation that sends close points to close points. And I can also undo it. Okay, so this is kind of your classic idea of the donut or the torus being the same as a coffee cup. Okay, so up here, we had our three surfaces of the sphere, the torus, and the two torus. And it's kind of useful to not draw these in 3 dimensions, but sort of remember that we can construct surfaces by gluing together the sides of a polygon. So for example, what I've got here is a solid square, and I've got my 4 sides, and I notice I've got the green arrows on this side. So what I want to do is just identify these 2 sides so the arrows match. And in doing that, I would end up with a cylinder, and I've still got the other 2 sides, like so. So I've glued together that green side. And then my next step is these other 2 sides. I'm just going to glue them together. So identify, glue this side here to this side here, so the arrows match. So I've got my 2 circles, and I'm just going to glue this to this, identify them. And what will I do once I've done that? I'm just going to end up with my torus. Similarly, the sphere, I can take a 2-sided polygon. So again, a solid 2-dimensional polygon. And I could just glue this side here to this side here so the arrows match. And in doing that, it's kind of like a purse or a handbag. And what I'm doing is just taking a zip and zipping this up. And when I do this, it's just going to fill out some sphere. Other classic example over here would be the Klein bottle. And just like the torus, I glue this side here to this side here. And that's going to give me some cylinder. But I notice that when I'm gluing these 2 red sides together, then the arrows point in opposite directions. So I've kind of got to make a little, I can't realize this in 3-dimensional space. So what I've got to do is kind of take this side here and go inside the shape and glue it like this. And this is going to give me give me a Klein bottle, which looks like this. Okay. So again, a lot of you will have seen these ideas of how to get the surfaces from polygons. Okay, so coming back to this sphere example here, one of the things I could do, so I took my disk, my 2-sided polygon, and I glued the sides together so these arrows matched. But I could change this construction and reverse one of the arrows. And this is going to give me the real projective plane. And again, this is a shape that I can't realize in 3-dimensional space. And kind of what's happening here is I've got my disk, and I'm going to glue this point here to this point here, this point to this point, this point to this point, and so on. And if you try and do this, you'll see that this will get really, really snarled up, and the shape would have to intersect itself in R3. And you get something you can't visualize without intersections. So here are some nice drawings of kind of what it looks like with some intersection. But the point is, it's terrible to visualize. So you need to remember that the real projective plane, which is an important example, is got by just gluing a disk. So the 2 sides kind of go in opposite directions from each other. And the importance of the real projective plane is that it's non-orientable. So what this means is that somewhere within the real projective plane, there's a copy of the Mobius band, like so. So where is this sitting? Well, if I look at this example up here, I could just take a strip like so and just color this in. And then if I deleted all of this white part, what would it end up with? I've got a blue strip, and I'm just gluing the 2 ends together with a little half twist to end up with this. So the real projective plane is an example of a non-orientable surface, whereas all of our original examples of the sphere, torus, and 2 torus, these don't have a Mobius band sitting anywhere in them. So these would be surfaces that are orientable. Okay, so far we've seen examples of the sphere, the torus, the two torus, and we could keep going with this pattern, have three torus and n torus and so on. And these are all orientable, and we classify them by something called genus. So the sphere has genus 0, torus has genus 1, two torus has genus 2, and so on. So basically, it's kind of the number of donuts that you've glued together to make your surface. You also get non-orientable surfaces. So we've got the real projective plane, which was our genus 1 example. But we could take two real projective planes and stick them together. And again, really hard to draw. So I'm just indicating how to construct this from your polygon. And this would be the two sum of two real projective planes. And that's a genus 2 non-orientable surface. Or I could take n copies of the real projective plane and just sum them all together to get some shape. And this would be a non-orientable surface of genus n. Okay. So the name to remember is the genus, which classifies either how many donuts you're made of or how many real projective planes. And just as an aside, to the genus in a non-orientable case is sometimes called the cross-cap. Okay, so we've got some examples of surfaces here. Well, what other surfaces are there? Well, actually, there aren't any other surfaces. So through these examples, we have every single surface possible. And this result is a classification of surfaces. And this tells you that any orientable surface must be homeomorphic or equivalent to one of your sphere, torus, two torus, and so on. And any non-orientable surface must be homeomorphic to the sum of n real projective planes, so all of these. So as an example, this Klein bottle from earlier is non-orientable, and that's equal to the sum of three real projective planes. Okay, so this classification of surfaces is really useful to have to hand, and we'll come back to this. One other thing we'll use is surfaces with boundary. Okay, so for a surface, what do we have? We have that each point locally looks like a copy of the plane or some open disk. But what can happen with surfaces with boundary is that we have some points that look like the half plane. So for example, if we take our annulus here and look at this point here, if we take a neighborhood of it, we're seeing the half plane. And again, this Mobius band example is also a surface with boundary. And I see my local, sort of locally, what do I get? I just get something that looks like a half plane as well. Okay. So I just noticed one question come in. Okay, so the question coming in was a good one that I was a bit sneaky about. And this was how I'm gluing the real projective planes together. And really the best idea, so the drawing I've got here is quite misleading. So the idea is really that I'm just going to take any two surfaces. So I could take my two real projective planes. Well, let's take a real projective plane and a torus, like so. So what I'm going to do is I'm going to just cut some region out. So I cut a hole in each surface, like so. And then I take some tube and I just join these two surfaces together. Okay, so this is a connect sum operation. So for any two surfaces, what I do is I cut a hole in each surface and then just glue those two holes together to get a new surface. And in these examples, all I'm doing is I'm taking this hole, so I'm actually just pushing the hole down to this point here. My picture is a little misleading. And there's no reason that you can't form this sum operation as we did here with respect to non-orientable and orientable surfaces, so the real projective plane and the torus. But whenever you do this, the classification of surfaces tells you you're always going to get one of the surfaces you've already seen. And in this case, we're going to get three real projective planes, but it's not necessarily straightforward to see that. Okay, excellent. That was a nice question. Thank you. Okay, so we were doing surfaces with boundary, and these will come up a lot. And the kind of the point is that even when you've got a boundary, you don't really have very much else going on. And the classification of surfaces with boundary, which is slightly less well known than for closed surfaces, is that every surface with boundary must be homeomorphic to one of our previous surfaces, so the sphere, the n torus, or n summed real projective planes, but with some disks removed. So all we can do is take one of our old surfaces and just poke some holes in it. So just to illustrate this annulus down here, what would I do? Well, if I just cut the top and the bottom of a sphere, I'm going to end up with an annulus. So an annulus would be the sphere minus two disks. And again, the Mobius band over here, we've already seen. And I could take my real projective plane. I could take my little strip down the middle that's going to form my Mobius bands. And if I look what's left here, I see that, so this side here would be glued to this part here. This part here glued to this part here. So after this gluing, what I've got is that this red stuff is one disk. Okay. So the Mobius band would be equal to the real projective plane, RB2, minus one disk. And the number of disks you've removed gives you a number of boundary components. So the boundary components, all you're doing is you're just sitting on the boundary and you're just walking around it. Oops, up the top there. Oh, I've messed up that example. Yeah, and then closing up. So the boundary components, so you're removing a disk and that just creates some boundary, and the boundary components would be the number of disks you've removed. Okay, so all you need to really remember is that with surfaces, they're kind of crude. What's going on is you're either orientable, so you're some number of copies, the sphere or some number of copies of tori, classified by genus, or a number of real projective planes. And again, the number of real projective planes is a genus. If you've got boundary, you've got holes in them. So then once you do this, I can start, I've got my surfaces, so I think, well, why do I draw the graphs in the plane? And there's no reason why I have to stick with the plane. So I can start drawing my graphs on any closed surface whatsoever. And the rules are exactly the same before, so my vertices become points, and my edges between them are just curves on the surface. And again, these curves can't intersect each other. So what I've got here is an embedding of the theta graph on a torus. Here we've got this example up here on the plane, but just on the torus. And again, something on the real projected plane, and remembering with the identification of points, it looks a bit strangely drawn. So for example, if this edge I travel along here, then that would take me to here, to here, to here, and back. So there's one condition we need we need to remember, and that's in a plane case, we're remembering that all of the faces were disks. And we insist on that for our surface case as well. So this is called a cellular condition, and these graphs are often called cellularly embedded graphs. And the idea here is that if I cut open my surface along the graph, everything must fall into a collection of disks. So this is an example of a valid embedding, but this would not be a valid embedding because if I cut the surface open along here, I would end up with a cylinder or an annulus, which isn't a disk. And again, my two embedded graphs are going to be equivalent if there's some homeomorphism of the surface, so if you like a deformation, that takes one graph to the other. So for example, this drawing here and this drawing here, these two embedded graphs are equivalent. Well, why is this? It's because I could take this loop here and just slide it all the way around the surface until it's drawn like this. But that would be distinct from that. And again, what you see similarly for the torus is even with this graph for 3 loops, I can still embed it in the torus, not only the sphere, and I can start getting inequivalent embeddings of it. So the final comment I want to make about this, before we move on, is that sort of the graphs in the plane are exactly the same as graphs in the sphere. And to do that, you can just do it through stereographic projection that allows you to move between plane and sphere in the usual way. And kind of the advantage of working on the sphere is you don't have this kind of awkward, unbounded region. Okay, so so far, just a review of classical things. So let's recall our 2 directions. So we've got properties of graphs, and we can embed them in surfaces. And we kind of have this choice of looking at kind of when graphs can be embedded, and think about graphs in the abstract. But instead of that, let's look at the properties of the graphs that already come embedded. Okay, so they actually come with a fixed drawing in the plane. And let's start approaching them by bringing together what we've got. So let's return back to plane graphs. So we've got our graphs drawn in the plane, and think about our 2 operations of deletion and contraction. So I'm going to start off with some graph drawn in the plane, or the sphere, which is more convenient. For my graphs, when they're actually embedded, I'll use this bold G. And for abstract graphs, I'll use the non-bold G. So you can always tell whether I'm talking about a graph or a graph that's actually embedded. And what I'm going to do is I'm going to take this graph G and pluck some edge from it. And then, just as before, well, I know I can delete edges of graphs by just removing them. And I can do the same with plane graphs. So I can get my edge here and just throw it away from the drawing. And I get another plane graph G deleted. Except this doesn't always work. There's kind of a little side condition here in that if E is a bridge, so that's going to be an edge whose removal increases the number of components, then if I throw this away, I'm going to get a graph of 2 components but I know that this is not a plane graph because my cellular condition on faces doesn't hold. So this unbounded face is not R2 minus a disk, it's R2 minus 2 disks. Okay. So what does this tell me? It tells me as long as I'm working with plane graphs like this, I can delete all edges except for bridges because it goes wrong. It takes me outside the class I'm interested in. What about contraction? Well, similar things happen. So I can contract an edge by taking my edge E I'm interested in, and then just identifying everything to a point here. So if you like, this is kind of a topological quotient space. So all of this line just gets reduced to a point. And again, because I started with something in the plane, I'll end up with something in the plane. And that works fine, unless E was a loop. So if I tried to do this construction on this part here, well, what would happen when I try and contract this edge? Well, let's see, okay? So here's my graph in the plane. I've got a green edge here. But the point is that when I identify this, so I'm pulling all of this green edge into a point, is that all of this stuff in the inside is going to get made up into this bubble here. And I'm going to have my plane and this bubble that sort of meets it at a vertex. So in particular, with the contraction here, I start up with something in the plane, and I end up with something that's not in the plane. It's going to be in a pinched surface. So with this, for plane graphs, I can delete non-bridge edges, and I can contract non-loop edges. And for plane graphs, that's absolutely fine, because these edges don't have such interesting properties. Okay, so I've got my two operations, and they look really different, but in actual fact, they're really the same operation, or more accurately, they're two dual operations. So this is my third construction for plane graphs. So what I've got here is I've got my graph in a plane, and I'm going to construct a new graph from it. And I'm going to construct this graph by throwing one vertex in each of its faces, like so. And whenever the two vertices or the two faces have some edge in common, I'm going to throw an edge between them. So let's put these in yellow here. I'm going to get one there. Oh, I'm going to get a loop coming around like that. Here's a face that's going to go around like so. What else? So this one will go around the back like that. And finally, I'll get that there. And then once I've done this construction, I get rid of the original blue graph. Like so. And this new graph in green and yellow is going to be my dual graph. And again, it's a plane graph. Something to notice is that if I start over here and do the same construction, then I'm just going backwards and recovering the graph I started with. So let's focus in on this construction. Let's just look locally what's happening at one of the edges, one of these blue edges in the primal graph G. And here's my edge. And then in forming the dual, what am I doing? Well, I've got two faces on each side, like so. I'm going to assume it's not a bridge because I want to delete it. So I'm going to get two vertices. And then my dual edge just get popped over there between these two faces. So in the dual. So I have these two pictures sitting on top of each other with the primal original graph, G in blue, and the dual in green there. And I can apply deletion contraction to these. So this blue edge here of the primal, I'm going to contract it. So these 2 points and this line are going to get identified. So I get this picture here. And for this green one here, I'm going to delete it. So I just throw that edge away and I'd get this picture here. But the thing to notice once I've done this is that if I was going to form the dual graph of this blue one, I would get 2 vertices here, but because this edge is missing, I no longer have an edge. So this is telling me that my G-dual deletee, which looks like this, is also equal to what happens if I take G, contract D, then take the dual, so doing this construction here. So what I've done is I've used duality to relate deletion and contraction. So this gives me a really nice identity that looks like this. But I also know that if I take the dual and do it again, I've done nothing. So I'm back where I started. So I could take this identity, dual both sides like so. And on this side, they're going to cancel out. So I just end up with G contract D is equal to G dual minus E, all dual. So kind of the important point here is that contraction can be defined in terms of duals and deletion for plane graphs. So if you're working with plane graphs, you don't really need to define contraction. You can just always work with duality and deletion. And this identity here, we're going to come back to. Okay. So maybe you don't need to remember it, but you should remember that there's some relation there. Okay, so that was plane graphs, but where we know we can just embed graphs in any surfaces at all. And this beautiful relation between deletion, contraction, duality for plane graphs, once you start applying it to graphs and other surfaces, kind of everything that could possibly go wrong goes wrong. It just doesn't really work, except in really, really special circumstances. So what happens is, well, duals can be constructed using the same idea in whatever surface you like. We just do this exactly the same construction. So each face, we throw a vertex, and whenever these faces are separated by an edge, we're going to throw an edge of a dual. So we've got one coming around the outside there, and we're also going to have another edge, I'll draw this in red, that comes around here, loops around the outside, back in like so. Okay, so my duality works absolutely fine, no problem whatsoever, but my deletion and contraction just don't make sense. And even a simple example, so this graph in a torus, a really simple graph, 3 edges, 2 vertices, I can't actually delete any of the edges. And the problem is that if I try and throw one of them away, like maybe this one here, then I've got a graph that is just not cellularly embedded. It doesn't satisfy this faces or disk condition. And it sort of gets worse when you think about it, even philosophically, in that for plane graphs, we could kind of avoid contracting loops. It wasn't really a problem for us because loops aren't that interesting in plane graphs. But once you're dealing with graphs in other surfaces, the loops are really, really important. So they encode a lot of topology. So what we've got here is we've got one graph that consists of a single vertex with 2 loops. But you see, depending on the surface and how you're embedding your graph in the surface, these can be very, very different topological graphs. It can go in the sphere, the real projective plane, in two different ways or the torus. Okay? So you can't really ignore what's happening with loops when you're dealing with topological graphs. But the good news is that we can fix all this. And to fix it, we just change language to ribbon graphs. And ribbon graphs have kind of a natural idea. And the idea is that we take a graph embedded in the surface, like so, and what I'm going to do is just thicken it up by taking a regular neighborhood. So I've got the graph sitting under there, and I've just, each point has become some disk, and each edge that was formerly a line has become a strip, a two-dimensional strip, or if you like, it's like a ribbon. And then once I've got this picture, I can get rid of the faces. Okay. So this graph here had one face, which went round the outside. It was kind of forming the torus. But I don't really need that to be there. So I could just delete all of the faces and just keep this green drawing of the graph, or the neighborhood of the graph. And what I end up with is my ribbon graph. So I can start off with a graph on a surface and end up with a ribbon graph. But I can also reverse this process by starting with the ribbon graph. And as a topologist, what is this? It's just a surface with boundary. And I know that my surfaces with boundaries are just closed surfaces with holes. So I could just fill in the holes in a unique way to recover my graph in the surface, or my ribbon graph in the surface, and then just recover the graphs in the surface. So this process is entirely reversible, and I can just move between my ribbon graphs and my graphs and surfaces there. So informally, my ribbon graph is just going to be a graph made up of disks with vertices, and my ribbons are going to form edges. Okay, so maybe something I should mention with my drawings here is that my ribbons here are kind of solid, although when I draw my ribbon graphs, I'm going to leave these empty. Okay, so these two lines, this is describing a solid shape. You can get a formal definition, but it's maybe not quite as helpful as this intuitive idea of just building a graph with your vertices being disks and your edges being ribbons. So we need to worry a little bit about equivalence, and we know that ribbon graphs are exactly our cellularly embedded graphs as before, so we want to consider them up to exactly the same equivalence that we normally would for cellularly embedded graphs. So we consider our ribbon graphs up to homeomorphisms that send vertices to vertices and edges to edges. So in particular, this means that we don't really care how the ribbon graph is drawn in the pictures in three-dimensional spaces. So for example, let's say this ribbon graph here, so we've got 3 cycle, 1, 2, 3 vertices, 3 edges. What I could do is I could take this vertex here and just flip it over. So I've grabbed hold of this, just flipped it over, and when I flip it over, I'm going to put 2 little half twists in the ribbons like that. So these are equivalent ribbon graphs. More generally, I could use sort of homeomorphisms. So maybe I could take this, I could cut that open, tie it in a knot, and glue it back together. But because I'm interested in things up to homeomorphism, I really don't care about this knotted part. So the edges can, the ribbons can pass through each other and knot themselves. So these would be the same ribbon graph. And again, sort of using homeomorphism, I could always add an even number of half twists or full twists to an edge. But the catch is that I can't add an odd number of half twists. So for example, these two pictures describe different ribbon graphs. And the one way to say that is, well, if I look here, this is a Mobius band, or this forms a Mobius band, whereas this would form an annulus. Okay, so ribbon graphs, they can be orientable or non-orientable. So we can start taking the properties of surfaces, so orientability, because topologically, what have we got? A ribbon graph is just some surface with boundary with some additional graphic structure. So we can start thinking about whether they're orientable or not. So it's going to be orientable if some cycle in it forms a Mobius band, like this one here. And we can start thinking of its genus as well, which is going to be just as genus when we think about it as a surface. So if I take this ribbon graph here, and if I were just to fill in the holes, I would find that I could put this on the sphere. This one would have to sit in a torus, so it would have genus 1. This one would have to sit on a real projective plane, and this is essentially Mobius band. Okay, so it's kind of hard to see this. So how can we calculate genus? Well, we can make use of Euler's formula. So possibly the most complicated parameter we need for this is the number of boundary components. So what I've got is my ribbon graph here, and I'm going to count the number of boundary components by just plonking myself down on the boundary and just traveling around like so. So there, so I've got a little half twist that go through there. Here we go like this, and there, like so, until we get back where they started. So this blue thing is going to be one boundary component, but there's another. So let's take this yellow pencil, and if I start to walk around, I would get a second boundary component there, and my third one, I can see I can go here. So in this example, this has 3 boundary components, and Euler's formula allows me to calculate the genus. So Euler's formula is V minus E plus F is going to be equal to twice the number of connected components minus a parameter called the Euler genus. And what the Euler genus is it's going to be, it's equal to its genus if it's non-orientable, or twice its genus if it's orientable. So the Euler genus of a torus is 2, and the Euler genus of a real projective plane would be 1. So let's apply this to calculate the genus of this example. So V is the number of vertices, E is the number of edges, F is the number of boundary components, K is the number of connected components. So what have we got? So my Euler genus is going to be equal to 2K minus V plus E minus F. So in this example, well, I've got one connected component, so I've got 2. I've got 1, 2, 3, 4 vertices. I've got how many edges? So 1, 2, 3, 4, 5, 6, 7 edges, unless I've miscounted. And I had 3 boundary components. So what have I got? So I've got, that's equal to 2. And I also notice, so then I have to worry about whether this is orientable or not. And I see in this example here that there is a Mobius band. So if I travel here, 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 and this, I'm going to get a Mobius band. So this is non-orientable. So that's going to give me my genus up there was equal to 2. So I can start working with these parameters without having to worry too much about what's happening. So the advantage of ribbon graphs is that, well, when things went wrong for graphs embedded in surfaces, they start going right when you're working with ribbon graphs. And deletion didn't work properly when you're working with embedded graphs, but it's no problem at all with the ribbon graph. And to see this, if I take a ribbon graph G and an edge, and for my G delete, what am I going to do? Well, here's my ribbon graph, here's my edge. I'm just going to throw this away. So for my G delete, I just get rid of the edge. And the thing to note is that there's kind of no problem here with loops and bridges and so on. But you need to be a little bit careful in that deletion does change the surface, or may change the genus of the surface or the surface that your ribbon graph corresponds to, and also the orientability of it. So for example, if I take this ribbon graph, 1 vertex and 3 edges, then if I delete E, I would get this one down here. And I see I can draw this on the plane, so this is going to be a genus 0 ribbon graph. On the other hand, if I deleted F instead of E, so I'm throwing away this yellow edge, I would get this picture here. And this ribbon graph, I could use Euler's characteristic, or I could realize I could draw this in the torus, and that would give me a genus 1. Okay? So kind of what's happening with this deletion is it's sort of changing the surface that the ribbon graph is embedded on. But then you come to the question of, well, deletion is easy. I just throw in an edge, but how should I define contraction? And in some cases, it's kind of obvious what you should do. If you're just trying to dream up a definition of contraction, one thing I could try and do is just identify all of the edge and its 2 ends. And sometimes I'd be able to do that, like this edge here, but sometimes I can't do it. I would get wrong, something would go wrong. So for this edge E, if I made the edge and its 2 vertices just 1 vertex, that'd be fine. But if I tried to make this vertex an F into a new vertex of the ribbon graph, I'd get a vertex that isn't a disk, so I'd get something that's not a ribbon graph. So there's not really an obvious way to define deletion for ribbon graphs. And it took a while to do this. And it's only recently sort of become clear how you should contract the edges of ribbon graphs. And by recently, in the last 5 years or so. And this all comes back to this identity we had for plane graphs. So recall that for plane graphs, we could define contraction in terms of deletion and duality. And for ribbon graphs, well, we've got deletion. And well, if we could define duals, we're pretty much good to go. So this is the approach we could take, is to define duality, define contraction through duality together with deletion. So what does duality look like in terms of a ribbon graph? Okay. Well, it's a really, really slick construction that relies upon this classification of surfaces. So kind of it starts with the observation. So if I was just going to form the dual that we saw before of a graph embedded in the plane, or let's make it a sphere because that's more convenient. So I throw 1 vertex in each of the 2 faces and the edges between between the faces whenever they're separated by an edge, like so. And kind of notice in this picture here is that if I blow up these blue vertices to fill in the faces, and these green vertices to fill in the faces, then my vertices of my primal, so in blue, my dual in green, and all of the edges define the whole vertex, sorry, the whole surface. And this is really the classification of surfaces, because what I'm doing is I'm taking my graph in a surface and just filling in the holes. So for my dual of a ribbon graph, I'm just going to do this process. So I take my ribbon graph, then I fill in all of the holes, because I know this is just a punctured surface, a surface with holes. So I can just patch in a disk here, here, and here. And then this example is going to give me this blue ribbon graph sitting on the sphere. And then all I have to do is just delete these two original vertices. And what I've got is a ribbon graph. A very weird drawing of a ribbon graph, but I can use homeomorphism to deform that. So I squeeze these down, each of these red things down into little disks, and I get a picture like that. So this is a really slick way of forming the dual. Hard to visualize in a lot of cases. But kind of philosophically pleasing. But it also has kind of, when you're viewing duality in this way, it has an amazing consequence. And you can make a really stunning observation about this construction. And what did I do in this example? Well, I looked at each missing hole, or I looked at the boundary of my ribbon graph. And for each boundary component, here, here, and around the back, like so, I glued in a disk. But my observation is that I don't actually need to use the whole of the ribbon graph. So rather than drawing or attaching boundaries to each edge, what I could do is I could choose some subgraph of it, such as this one in red, and then just glue the faces to the boundaries of the subgraphs, like so. And then, when I delete these two original vertices, I'm going to get a new ribbon graph. So let's see this picture. Oh, let's see. Hopefully I put this picture. So let's see this in process down here. So what I've got is a picture of a ribbon graph, like so. And I'm going to pick some subgraph, and my subgraph is going to consist of all of the vertices. And I'm going to just take these two edges here. Now, this subgraph, it has a boundary, which is highlighted in red. So two boundary components in red, like so. And then to each of these boundary components, I can just fill them in with a disk, so with two disks to glue them in. So this would give me this picture here. So what I've got is I've got a graph in the sphere, or a ribbon graph in the sphere, but I've also got this little handle here that corresponds to this edge. And then, just as before, I throw away my two original vertices, my two blue vertices, and what I end up with is a weird drawing of a new ribbon graph that I can tidy it up. So this process, which admittedly it's hard to visualize at the moment, gives you what's called a partial dual. And the idea of a partial dual, which is due to Sergei Shmutov from 2009, is that really you want to form the dual of the ribbon graph, but only with respect to some of the edges. So if I take a ribbon graph and I take some subset of its edges, then my partial dual G to the A, so the A will be the set of edges I want to dualize. I obtain this by looking at the subgraph on A. So in this example, a subgraph formed by these yellow edges, these yellow shaded edges. Then I glue in disks to the boundary and just delete the original vertices, and I get a new ribbon graph. And I don't know about you, but I find this process very, very hard to visualize. It was okay in this example because it was kind of easy and you're putting on a sphere, but it's kind of hopeless to construct generally. And I'll show you how you should really be wanting to construct these in the next slide. But maybe I'll just mention, so my basic properties of partial duals are, well, if I dual every edge, so G raised to the power of the whole of the edge set, that's just the usual dual of a ribbon graph or of an embedded graph in the surface. If I form the partial dual with respect to the empty set, I haven't really done anything, so I've still got the graph I started with. The genus can change when I form the partial dual. So for example, up here I had something with genus 1 and ended up with something with genus 0. And that's unlike the full classic dual where it must be the same. However, orientability can't change. The relation, so if I dual some edges, then dualize some other edges. So I dual with respect to the set A, then the set to the set B. So whenever I dual an edge twice, I'm back where I started. So I'm going to end up with the symmetric difference here. And this means in particular that I can always form the partial duals with respect to one edge at a time. So kind of fast properties, we'll see them in action soon. So how on earth should I compute these? Well, you definitely don't want to be computing them in the way I said. Okay, so let's do this in example. So let's form the partial dual with respect to this edge little a here. So what I'm going to do is I'm going to we'll consider the boundary cycles of my spanning subgraph like so. And I'm going to have two of them. I've got one of them that comes around this edge I'm going to do, and the other one is this isolated vertices. What about these blue edges? Well, they're not edges I want to dual, so I'm just ignoring them. So my first step is look at boundary of my subgraph formed by all of the vertices and the edges I want to dual. My next step is to add some arrows. And I'm going to add an arrow here and an arrow here pointing in opposite directions. I'm going to call those A. So whenever I have a dual edge, so let's just say add. So I'm going to do this for each edge that I'm dualing. What about these missing edges? Well, I do the same process. So I travel around the edge, and wherever they meet my boundary component, I'm going to put a pair of arrows. So I'm going to get an arrow there and an arrow there. So that's going to be my A, my B, two B arrows. And also, I do the same for this. So I travel around the boundary of my edge, decorate with arrows. I'm going to get two C colored arrows. So in doing this, what have I got? Well, I've got two circles. And I see, well, as I travel around, let's decorate these with the arrows. So in this one, I've got a B arrow that way and a C arrow the other way. And traveling around this one here, so I'm going to get my A arrow. And so and then the C arrow is going in the other direction. So that's my C. Then my A arrow is with the direction. And finally, this B arrow is going to be there. And this system is what's called an arrow presentation, and it describes a ribbon graph. So what I do here is I just fill in the circles. And by doing this, these circles become disks, okay? And these disks are now the vertices of my ribbon graph. And my next step is I'm just going to add the edges by connecting up the arrows. So I'm going to have one edge, A. So I'm going to just come out, follow A, and then add an edge going round, so out of the head into the tail of the other A, along, then out, and then just join it up to the arrow for my B. So I come out of here, into this arrow here, along like so. And my C, I'm going to come round like this. And I notice I'm going to get a little half twist in there, which tells me that I've made a small mistake. Yeah. So I come out of C, go around, connect to the tail of my other C, go along, come out like that. And then what have I got? I've got my new ribbon graph. So I just glue in the ribbons, and what I end up with is my partial dual of G raised to the edges. And this process is much easier than the definition. In fact, for the previous definition, had little hope in calculating all but the simplest examples. But this one here, it's kind of routine, it's very combinatorial. So to run through this again, so you look at the boundary cycles of the subgraph formed by the edges you want to dual. You decorate them with arrows where they touch edges. So for the edges that are in, you're going to have that pairs of arrows here. And if they're out, you're going to have pairs of arrows here. And then this collection of circles with arrows, you can obtain a ribbon graph by just filling in the holes and adding and gluing in the ribbons to the arrows. Okay, so we now know how to delete edges. We also know how to form duals and partial duals. Okay, so we could form the dual by just partial dualing every single edge of the ribbon graph. And remember, we're trying to describe contraction. And our plan was going way back to this definition of plane graph contraction in terms of duality. But we can take this and with the power of partial duals, we can start tidying this up that we couldn't formally do when we're working with plane graphs. And we've got a nice little manipulation. So we wanted to find contraction by dual, delete, then take the dual. So the dual I'm just forming the partial dual with all of the edge sets, so I can replace these stars with the edge sets. This edge set here, so this consists of my special edge E and everything else, so I can separate that off as a union. So all of these edges, these are so standard properties of partial duality is I could take all of these edges here, and because I'm not deleting them, because I'm deleting E, it doesn't really matter whether I form the dual and then delete or delete and form the dual, so I can move these outside. So what I've got a partial dual with respect to E, then delete. Then I'm double dualing everything else, but double dualing does nothing at all. So overall, what I've got is my G dual delete, all dual. I can define it locally just in terms of partial dualing and delete. So this gives me my definition of contraction. My definition of contraction in terms of partial dual and edge and deleted. And kind of, this has really unexpected properties. So often it would behave as you expect. So I'll just do some, so if this was my G, then if I contract E, what would happen is my ribbon graph, all of this when a partial dual would get identified and then delete would get identified as a single vertex. So it would end up with one single vertex, and I've got my edge F coming around like this, and my other edge comes around like that, so get something on a torus. Whereas what would happen here is if I go along, then and figure out what this was, when I do the partial dual process, I'm actually going to create a new vertex. So by contracting the edge F, what I would find is that actually I'm going to end up with a path of length 2, which is really unexpected and not what you'd expect from traditional graph theory. And it kind of goes on a little bit more. So if I wanted to contract this unique edge of this one vertex, one edge ribbon graph, if that was my G, sorry, this is my G contract F, and that was my E, my G contract E, I'm going to end up with 2 isolated vertices. So the number of components is changing under contraction. So the point is that this is doing something totally and utterly different from the usual graph contraction you're used to working with. And then with this, you can start doing minor theory for ribbon graphs. So you can define a minor as any ribbon graph is obtained through, well, we've got edge deletion and we've got edge contraction. So we can start deleting and contracting edges as well as vertices. Or maybe since contraction is a special case of deletion and partial duals, we want our minor to be deletion and partial duals, and there are often special times to do that. So maybe very quickly, let me take you through just a quick example of how to do this in the few minutes I've got left. Is if I had a problem and I noticed that when I'm partial dualing some ribbon graphs, I sometimes can result in a graph that is of genus 0, so something that's on the planars of the sphere. But sometimes I can't. So no matter what partial dual I do for this ribbon graph, I'll never get something of genus 0. So I could look at the problem of characterizing all of the ribbon graphs that have some partial dual of genus 0. So how can I do that? Well, so let's come back to this formula for the Euler genus, which was our V minus E plus F, so vertices minus edges plus number of boundary components. So that was our Euler characteristic. And then the Euler genus was just twice the number of components minus this parameter. And in the problem set, one of the problems is to work out the Euler characteristic of a partial dual. And if I want a partial dual with respect to A, the Euler characteristic is just going to be that of G restricted to A, so just include the edges in A, that of the ribbon graph given by throwing away everything but, sorry, by throwing away the edges in A, and then minus 2 times the number of vertices that these two graphs have in common. So if G has one vertex, and I know that I'm getting something that has genus 0 afterwards, then it can only have one vertex in common. My partial dual gives me genus 0. So I also know that through Euler's formula, that my two ribbon graphs, given by restricting the edge set to the ones I dual and the ones I'm not dualing, must also have genus 0, so they must also be plane. So this gives me a partition of my ribbon graph into two types of edges, into two parts that are both plane. So the blue edges are the ones I'm dualing, the yellow ones are the ones I'm not. And that's kind of a very specific structure. And what I can do, and this tells me a lot. So with my ribbon graph from the example, I could form the intersection graph by whenever I have a pair of edges that are interlaced like this, I'm going to record that happens, and I'm going to record it in a simple graph. So I'm going to take one vertex for each edge of the ribbon graph, and whenever two edges intersect, I'm going to throw an edge between them, or two edges interlace. So A is going to interlace with E, so I get an edge there. My B interlaces with E, like so. My D interlaces with C, and also my E interlaces with C. And in doing this, what I've ended up with is something that is bipartite. Why is it bipartite? Because the two parts of my decomposition are planar, so they can't have any of this interlacement property, otherwise they wouldn't be of genus 0. So this tells me that any ribbon graph of one vertex has a partial dual of genus 0, if and only if this intersection graph is bipartite. So this means that if any partial dual is not of genus 0, it's going to have an intersection graph that is not bipartite. What do we know about bipartite graphs? Well, a graph is bipartite if and only if it has no odd cycles. So if it's not bipartite, my intersection graph must contain an odd cycle. And then if the intersection graph contains an odd cycle, that means that my original ribbon graph must contain something that looks like this. And the idea here is that all of the edges are interlaced. All of the edges are sort of interlaced pairwise. So you have this sequence as you go around and get interlaced pairs. And contracting all but 3 edges would give me this. So what this does, it gives me an excluded minor characterization of when a ribbon graph would have a genus 0 partial dual. And that's going to be if and only if it has this special one that we derived from this analysis. We've got this one to ensure that it's orientable. So if it's got that somewhere As a minor, it must be non-orientable. And finally, we had this one vertex condition, but by considering all of the partial duals of this, we can get rid of it. And this would give us a third minor. So we've got an excluded minor characterization of when a ribbon graph would have a partial dual of genus 0. Now, in graphs, we know that every minor closed class of graphs can be characterized by an excluded minor characterization. And a nice big open problem that I'll end on, is this true for ribbon graphs? Or even find an excluded minor characterization for ribbon graphs that have genus 2 partial duals. And that's going to be a hard problem. And I think with that, it's time to stop. I've overrun by a couple of minutes. So thank you very much.